Hello everyone. I would like to welcome you to class of discrete computational structures. In this course, we are going to deal with discrete mathematics and how it can be related to computer science. So we will try to cover all the necessary information we need from discrete mathematics in this course for sure. The first thing I want you guys to do is to go through course syllabus carefully. It contains useful information such as the textbook or uh, the related topics that we are going to cover during the semester, and also your grading distribution. So let's start with lecture 1. Lecture 1 is related to logic and proof, and we are going to finish it until the end of next week. So for 4 sessions, we are going to talk about logic and proof. But what is logic? The basis of all mathematical reasoning is related to logic. And that's the beauty of mathematics, because when you are proving something, then if it is proved, then nobody can say, for example, it was wrong or something like that, because it was based on logic. And if you want to define new spaces in mathematics, then okay, you can define new theorems inside that environment. So we should know about these terms, logic, proof, and theorem, to make everything sense for us related to mathematics. So each book of mathematics should start with logic. Otherwise, they mention you should know it before starting this book. So as we said, the basis of all mathematical reasoning is related to logic. And to understand mathematics, we must understand what makes a correct mathematical argument. That's why we need the proof for each one of them to be evaluated and say, yes, this one is proved and we can use it later. And once we prove a mathematical statement is true, whenever this is true, whenever we prove it, we call it a theorem. And you will see them a lot inside mathematical books. So there are some applications of proof in computer science. I mentioned 3 main ones, which also mentioned in the book. This book is very well written, fortunately, the book that I uploaded on O2 class for you. And I tried to design most of the slides based on the book. So if you read the book carefully, I'm sure it will be very easy for you to understand about discrete computational structures. All right, so as I mentioned, I listed 3 main ones for you. Testing algorithm, for example, we want to see whether the desired output can be reached, and proof can be very helpful for that. And especially artificial intelligence these days, we need to use proof for that as well. You can see some examples in the book related to them, which were written. And let's start with an important definition here: proposition. So proposition is a declarative sentence that is either true or false, but it cannot be both. Let's understand it through these examples. Like, Istanbul is the capital of Turkey. So is it true or false? Obviously, this is false, right? So it can be either true or false. At the same time, it's not happening. Like 2 plus 2 is 4. Yeah, this is the case. This is true. 1 plus x is 4. This is a linear equation. And this is not either true or false. We cannot say anything about it. So this is a proposition. This is not a proposition, and this is just the equation. Like, I know x is equal to 3, so what? This is true or false? We didn't ask about, for example, what's the value of x, whether this is 3 based on this equation or not. It's just an equation, and we don't know whether this is true or false. We don't have a proposition here. And about next one, just a question. What are you doing? And this is not a proposition. Okay, So the first two were propositions, but not these two. Down, please. This is a command, and no, whether this is polite or not, then it doesn't matter. It's not a proposition. We cannot evaluate it whether this is true or false. So I think you got the idea. Whenever we have proposition, we should know that this sentence or this statement is true or false. Then we call it a proposition. So what is the negation of a proposition? If we denote proposition by a letter like P, then negation of that means that if P is true, then negation of that is false. If this one is false, then the other one is true. That's why we need a table to simplify it. For example, a truth table can be used in order to show whether a proposition is true or false, because later we will have compound propositions and truth table can be useful for them. This is a primitive method for sure. Later we don't use it. We need theorems in order to show whether a statement is true or not. Otherwise, this is just for practicing, and later we will see at the end of this lecture, I will show you the application also we can use in computer science. All right, so this is a truth table. It shows that, for example, for P, we have two different options. Either this is true or false. And negation, we can show it like, if this is true, this one is false. If this one, P, is false, then this one is true. Guys, would you please excuse me? I will come back in 1 minute. They are fixing water now, as you know, in the campus. Let me check something. I'm coming in 1 minute. Okay, I'm back. Sorry for the pause. Now, let's continue with different compound propositions and the operations that we can use between our propositions. One famous one is the interception. So this interception, we call it conjunction of propositions. So P and Q. You already, I think, familiar with these logics anyway, but anyway, let's go through them one by one at this one so that we cover all of them. So P, we can have, with the combination with Q, we have 4 different scenarios, like P can be true or false. But at the same time, when P is true, Q can be either true or false. So what's the idea of conjunction? It says that both of them should be true. You see, both of them should be true. Otherwise, this is a false proposition. If, for example, one of them or both of them are false, the conjunction will be considered as false. So you see, truth table could be very useful to check all the scenarios. The next one, disjunction of propositions. It acts like union in a statistic, right? Then last one can be considered as interception or AND logic. This is OR logic or union in a statistic. So in this case, we say if either one of them or both of them are true, then the disjunction will be true. Only in one case this is false, and this is the case that both propositions P and Q are false. Sometimes we want to make sure that if only one of them is true, then we want to include that this is true, not both of them. In that case, we consider the exclusive OR, and we denote it by this sign. So you see, in that case, at least, I mean, one of them should be true. If both of them true, even this is false. Either P is true or Q is true. Otherwise, if both of them true or both of them are false, then we say this compound proposition is false. Actually, they are not compound yet, because later I will show you what compound proposition would look like. At this time, we just have a operand between them. So what do we mean by conditional statement or implication? So by implication, we denote it by this sign, and we have either P or Q propositions. In that case, let's see when this is false. This is false only if P is true but Q is false. You see, even if P is false and we reach the true value for Q, again we consider it as a true value for this implication. So this is sometimes confusing, and I will show you about the biconditional statement that is different in that scenario. So you see, P, if it is true but we get false for this, then that's the time we reach false. Like usually in our regular statement, we will see if and then whenever we talk about implications, and obviously you saw it in different examples before. Otherwise, the book explained it perfectly. Right, there are some terms that we should know, like converse, contrapositive, and inverse. Assume that we have such an implication. P implies Q. You already know about it now. So if we talk about converse of this implication, it means that interchange the place of Q with P. You see, Q implies P. This is what we call converse. Contrapositive, it means that negation of Q implies negation of P. So we show it like this. And later, I will show you these two are equivalent. And inverse. Inverse shows that negation of P, negation of Q. Just apply negation to both sides without interchanging their place. Okay, so we should know about these three terms, and we use them a lot. As an example, when we talk about equivalent, it means that two propositions, they give us exactly the same truth and false value in the truth table. If this is the case, we call them equivalent. And we can prove that these two are exactly equivalent using the truth table. You can practice it by showing that this is the case. And for biconditional statement, we have such implication that both sides should be true or should be false so that the whole statement is true, like this. This is true if both of them have the same value. If they differ, then in that case, it is considered to be false, right? So both of them should be the same. That's why when we say equivalent, you can also use such a statement too for two equivalent propositions as well. Now, when I talk about compound proposition, it means something like this. We have combination of them, and in order to construct it, truth table could be useful at primitive level. Later, we will learn how we can deal with it without using the table. So in order to find the truth or false value of this statement, then we need to solve it one by one. And that's why we need to know about the order of, for example, negation. This one should become before disjunction or not, and we can use this table. This shows the order. Like negation comes first apply this, then consider disjunction, conjunction, and then implication. So by using this table, we can solve it. So first you see negation. So let's try to find negation of Q. So whenever we have true, you should consider false. Whenever we have false, true. And you can construct the rest for negation of Q. Now when we have disjunction like this, it means that either one of them should be true or even both of them. So let's see. This one is true and this one is false. P is already true. So one of them is good enough to consider this one true. Only in one case, it could be false. And that's the case both of them are false. You see, when this is getting compound proposition, we may make mistakes, but as you can see, the logic is very simple. So conjunction, both of them at the same time should be true, otherwise it should be false. You see, only in this case you can see both of them are true. So at last we can find the truth or false values for this compound proposition, and for that we should consider this disjunction, whether this implies to the conjunction of P and Q or not. This part and this part. Okay, this one is true, this one is true. For sure this is true. And this one is true, but it will result into false. And that was the case that we could always say that this implication is false. In other situations, other combination, it was always true, right? So this one should be true. Whenever this is true and this is false, that's the case. And again, you see, we have only one this situation that we get false for these compound propositions. Now, what's the application in computer science? In computer science, as you know, our programming languages, especially the one that we call machine language and the basic one that computer understands us, using 0 and 1s, because we define everything in terms of bit. So this is a binary sequence that we usually have on our computer. So just convert false to 0, for example, and true to 1, and that's it. Very easily we can apply it to computer science. So whenever we are dealing with such operands or compound propositions in computer science, we can easily transform everything into 0 and 1s and solve it. And in one assignment that I will give you 2 weeks later, most probably I will include one question regarding this to see how we can compare two sequences, including only 0 and 1s together, and come up with the truth table like this. And later I will show you, you don't even need a truth table to solve them. If we will have corresponding topics, for sure I will cover that as well. Okay guys, so that's it for today. For next session, I will talk about the other parts of this proof and logic, and hopefully if you go weekly with it, as you can see, it's very easy. It's get a little complicated after a while, but if you go weekly with the course, I'm sure there will be no problem. Okay guys, so if you have any questions, please ask me now. Otherwise, you can send me email, and as I said, within 48 hours for sure I will answer all of your questions.